let us start. So I assume my screen is visible. तुषार screen दिसतोय ना?
Yes, sir.
Okay, thank you. So that day we wrote a program using assembly. So the program was meant for say pgm2.asm. So we wrote this and we tried identifying how exactly this gets translated. The data part as well as RO data as well as this BSS. Fine. So we'll be moving further and we'll be trying to really find out what exactly happens at that end when we do really talk about instruction. So one by one we are going to talk about instruction. Now to do this we would be requiring something called as Intel manual. So I assume you must have seen our what you can call it as Moodle course, okay, available on Moodle site. Okay, so if you see there, like I assume I have added link to Intel manual. So can you open that? See Moodle, open Moodle platform, download that Intel 32-bit manual. Below the assembler and loaders book, you can see that I have added that link over there. You can download that PDF. So I do have it with me. So let me open that. Okay, so it is better to go and download it. So if you see, this is the manual that I was talking about. So let me open this. New window. So I am assuming that each one of you should download this. Okay, because we are going to make use of most of these most of the pages in this particular from this particular file, the PDF. Okay, so let me open that. So like we are going to make use of few pages from this particular book. So go to chapter number 2 and see this page. Okay, so right now even if you don't open it, but it is available on the screen. Can you see this instruction format? Each one of you. Okay, now there would be different 6 parts included in the file. Sorry, in the instruction. So when we saw like when we saw this LST code, like for example, when I said p.lst, so one could see that like we can see the size is varying. So this is for my first instruction. This translation was meant for a first instruction called move byte of A. This is my second instruction. Whenever I see dash, ultimately it is continuation. So when I see this instruction, correct, this instruction was translated here. This is my third instruction, which is translated here. So there is no consistency in respect of saying that, okay, now you have same number of bytes. So as per Intel 32-bit architecture, your instruction is 32-bit instruction. Correct. So like even for 64-bit majority number of times this would be used. So now you have instruction prefixes. Okay, this is optional one. It is like reserving 1 byte to represent this. There is opcode. This opcode can vary from 1 byte to 2 byte to 3 byte. So it could be of either of the size. then we are going to see mod rm, which basically tells you like what are the operands with the instruction. Now, whenever there is memory reference, this memory reference, then this would be called as SIB, scale index base. Okay, this also is 1 byte. So these are if required. By default, you would be seeing that there would be opcode involved. Okay, even displacement, we are going to see this displacement part. So this would be 1 byte, 2 byte, or 4 bytes, or none. So either it would be there or it would not be there. If immediate value is there, immediate I mean to say when you write move ex comma 10, so then it would be going here, correct? So it would be organized as 1 byte, 2 byte, and or sorry 4 byte. So depending upon whether does it have say any operand where it would be requiring that kind of stuff ultimately. That's how it would be decided whether which one we are going to make use of, whether we are going to make use of displacement or immediate. Correct. So these would be the 6 forms, or these would be the 6 components of every instruction. Further, these 2 bytes mod rm as well as SIB would be divided into subsequent set of bit positions. Okay, so this bit position for mod rm would be divided into like 3 groups. So if I talk about from least significant bit to most significant bit, so from 0 1 we will see rm, from 2 3 sorry 0 1 2 we will see rm 3 bits, then range of code this would be 3 bits, and mod would be 2 bits. Okay, so let me add that. So I'm talking about mod rm byte. So this is a byte, correct? A byte divided into 3 components. Okay, so this would be like 1 2 3 4 5 6 7 8. So these 3 would be dedicated for something. These 3 would be dedicated for something, and these 2 are dedicated for something. So now when we see values over there, what would be possible combinations? So like for example, if I really pick them, so 0 0 0 0 0 1 2 3 4 5 6 7 8. Okay, so all possible combinations can be seen like this. Correct. So but because considering that 80 bits, but in this case, when I separate it, after separation, I can see that like if I don't consider these now, say these are not there at all. Let us not concentrate on this. Let us concentrate on these 2 bits. So these 2 bits would be having possible values to be like this. Correct. So 0 0 0 1 1 0 and 1 1. They would be used depending upon what kind of format is followed by the instruction. Similarly, when I do talk about these values, so if I pick this 0 0 0 3 bits, so I can see that it would be like this 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, and then lastly 1 1 1. How many values are there? 1 2 3 4 5 6 7 8. Correct. Same thing would be replicable over here, replicated over here for each position for these last 3-bit positions. So that's how your mod RM would be. So when I say how many mod values are there, so mod will have 2 bits, which would be from MSB side, most significant bit side. Bit number 6 and bit number 7. Bit 6 and bit position 7. Okay, they would be having these 4 values. So your mod can be possibly of 4 types: 0 0 0 1 1 0 and 1 1. Now your operands, depending upon operands, this decision would be taken whether I am going to have which value among these 8 values. Among these 8, what would be my value here? Same thing would be for this bit position from 0 1 to these would be 8 values. Among those 8 values, what would be the possible value for that bit position? Correct. So if I have to like group it appropriately, then my mod would be divided. My mod rm byte would be represented by 2 bits. Say for example, let me show you the part of code. So if I say this is my opcode, okay, then this is my mod rm byte. Okay, then this might be addressed for this A, and this A is translated to 61, small a, because small a is 97. If I translate that, I assume it should result to 61. Now if I see here, I have used move. Okay, so earlier it had C6. I can see that it is C7. Correct. Now I am having the same, like you can see here 0505, because if you see form for both the instruction is same. What exactly you are trying to move? You are trying to move a value which is an immediate value. So this is immediate. This 61 and 73 is used for A and S. The 61 is used for this A. Now when I wrote move dward, so you can see C6, C7, C7. Now if both of them are C705, even if this is C705, what would be difference between them? So this is taking a 16-bit data, this is taking 32-bit data. And that's why this 66 is playing a role, important role here, called as prefix, which was part of our instruction set. Okay, so if I see what are the instruction prefixes, so let us see those instruction prefixes. Now try to say whether can you see 66 over there. Consider the group, this group 3. Can you see 66? Yes, please. Correct. I'm assuming you are getting what exactly I'm trying to tell. Yes. Am I audible?
Yes, sir.
Okay. Please respond
Yes.
so that I can know whether you are there. So if I have to see this, how exactly this 66 should be used. So let me write a simple code. So let me say a max first dis dot asm. So I specifically will target now only because we already have addressed dot data and dot bss. So let me target this dot text section dot text. So let me write global main. Let me write it like this: move ex comma ebx. Okay, let us take different word ecx comma edx. Now I am writing this. I have written as 32-bit registers. Correct? These both are 32-bit parameters. So what should I do now? If I want 16-bit data, then I will write like this. If I want 8-bit, then I will write like this. Correct? Now, if you see, both of them are like all three of them are doing some operation which is moving the data from one register to other. Now, in this case, whenever we are talking about this move instruction, it is like this: move destination comma source. So source is this second parameter, and destination is this parameter. ECX would be destination. In this case, CX would be destination. In this case, CL would be destination. Now value from EDX, DX and DL would be source. Now if I try to translate this, okay, simply do this. And more frequently we are going to make use of these instructions like this thing only, whatever I am writing now. So first underscore dis dot asm dash l p dot lst. Okay, so I am saying that there is an error at line number 4. So let us check. 1, 2, 3, 4. Sorry, this should be commented because I am writing two instructions in one line. So it is this form. Move is having this form. Move means what? Change like move the value, like store the value kind of thing. Sorry. Nasser. So our code got translated. Now let us see. Now what difference can you see in all these three instructions? They are varying in what are the number of bytes represented to see the machine code. This instruction move ECX, EDX required 2 bytes because I said this is 1 byte, this is second byte. Same thing was written here 89D1. Then this 66 is telling me that it is a 16-bit operand that I am using currently. And for 8-bit, you can see it is completely different. D1 was taken as it is. If you see, D1 was across available because my registers are basically using C, ECX and EDX, either 16-bit version, 32-bit version or 8-bit version. All of them are from that bit position. Now, if I talk about this 89, so let me go to this instruction manual, this Intel manual. Try to see this move. So if you see chapter number 4, okay, try to find out their move instruction. So if I go to 4.3, let us find move there. So let me scroll down this a bit. Let us see this move. Yeah, we got move. See how many variants are there for move. Now what are the numbers that we got here? 89. So let us see 89. Where is 89? See both these places. 89, 89. Can you see 89, 89 at both places? Yes.
Yes, sir.
Okay. Now what might be the reason? Like it is adding 88. Sorry, 89. You see here it says move RM16, R16. So your source is R16. In this case, your source is 32-bit. Register 16 or register 32-bit. R16 means register 16. R32 means register 32. Size. Okay. Then you may have memory or register with 16-bit value or with 32-bit value. And it is having slash R. So this slash R also will be playing an important role. Now, how many variants are there for move? So these many. See there. So if it is immediate, then it is going to have something like this B8, B8 plus something, B8 plus something, correct? For R32. This also is having something, but we are not anyway concentrating on 64-bit. Either would be talking about 8-bit, 16-bit or 32-bit only, not 64-bit. So these all are variants of your move instruction. See how many types are there which can be used depending upon what are its parameters, what are its arguments at that point of time for your operating system. Sorry, for your instruction set. Fine. Now, when you really see this, will it be same for my add instruction as well? Let us move further. Okay, so okay, let me do this thing. So what I will do is I will open this code. I will simply take these three and I will replace move by add. Correct? Yeah, you can see I have added this. Add ECX, ECDX, add CXDX, add CLDL. I only changed that from move to add. Now let us try to translate this. Let us see the code. Can you see the difference? What is same? What is different? Read it and let me know. Yes. Where is the
Cell
difference?
prefix. Cell
Sorry.
prefix 66 is same.
Okay, good. Very good. If it is a 16-bit one, correct?
Yes, sir.
Okay. What is the next thing? What is common in between?
Sir D1.
D1, which is telling that your operands are same. Correct? What is changing now? At some places it is different, at some places it is same. This 89, 89, 88, 01, 01, 00. So this is opcode. So if I go to this add instruction now in my manual, so let us see this here add. Let me go here. Let me pick add a double D. Yeah, same format that I saw earlier with respect to move. Similar kind of format is there. So like the things were what 0 1. Let us try to see where is 0 1. See 0 1. It is having the same format. Add RM32 R32, which was similarly there for your move instruction as well. Am I right? It was like this only. Only that move was replaced by add, and that's why one can see here 0 1 for add, and for move it was 89. Let me show you move again one more time. Yeah. Now see move. RM32 R32. Okay, where it is? Yeah. See this one. It was same RM16 R16, RM32 R32, 89. And for it, for add, it was 0 1. Only 89 was replaced by 0 1. Move was replaced by add. Rest of the things were same. Instead of move, now it was add. Correct? Correct? Now, when you say this, ultimately, how exactly these numbers are formed? So at least one can conclude saying that every instruction would be having something to represent. So let me replace now. Let me add few more instructions. So let me cut them. I am replacing this move by now sub sub sub. Here I am changing this to CMP CMP CMP. This comparison subtract add move. Okay, let us see the code. Now see again what is same, what is different. D1 is across same. Can you see that? 66 was used because at 4 places we have used 16-bit registers. First place, second place, third place, and fourth place. So that's why this 66 was occurring 4 times. D1 is same across. So ultimately, no matter what your instruction is, whichever the instruction asking for 2 parameters, asking for 2 operands, if both of them are registers, in across these 12 values, 12 instructions that we wrote here, totally 12 instructions we wrote, which are different one. Now how system identifies them differently. So to differentiate between these operands, it is making use of something called as D1. But whether it is 16-bit or 32-bit, that would be decided by this 66. That would be decided by this 66. Now whenever time comes to talk about 8-bit registers, now you have completely the different opcode. Opcode is one mechanism by which your instruction is identified at the architectural level, your processor's architecture level. Correct? Fine. Now next. Now if we have all these operands same, what happens if I change the registers? Now here I will write say EBX comma EAX, BX comma AX, BL comma AL. Here I am writing EDX comma. Now I am changing that EDX CX, only position. DX CX DL CL. In this case, I will change it to EAX EBX AX BX and AL, BL. So let me group them so that it would be easy for one to differentiate that part. So let us add this to separate them out. You can see now first six are having same parameters. I mean to say first three are having same parameters in the sense of same registers are there. Only size is mattered. Secondly, only I change the operand order with along with the other instruction. Third thing, I have other set of operands. Now in fourth group, I have changed operand order. Is that fine? Now let us try to see how exactly it changes. Now D1 is fixed for only this part. Now this is represented by CA, CA, CA. This is represented by C3, C3, C3. This is represented by D8, D8, D8. Now whatever are thing that I earlier saw, these operands never, these opcodes haven't been changed. Like 89, 89, this 88, correct? 29, 29, 28, 01, 01, 00, 39, 39, 38. These remain same. What changed was that D8, C3, CA, and D1. On what basis this would be decided by the system? So let us talk about that mod RM. Now for this purpose, we'll require to go to page above page. So go to instruction format page. Now try to see page number. I think as per this numbering, it should be 32. No, below. Yeah. Let us see what it. Yeah. So it talks about mod RM. So it says mod field combines the RM32 possible 8 registers. 24 addressing modes are there. That's how that mod is decided. 00011011. Range opcode. Purpose of range opcode is field is specified in the primary opcode. Bits opcode information. RM code, RM field also specifies operand type. Correct? Let us go below. Yeah. So now I am talking about this page. See, this is page number as per document. It is page number 40. Can you see the registers here at the top? Can you read that for me? Somebody, please. Can somebody read that for me? What are they? Let me see. Until unless I take none. Kanchan, are you there? Kuvar Kanchan.
Yes, sir.
Okay, read what are the registers that you see at the top in last 6 columns. No, not 6, 8 columns.
Sir, AL, CL, DL, BL, AH, CH, DH, and BH. These are for
Correct.
8 bits.
8 bit, correct, good. Now if you
Then
see, one minute. If you see this AHAL somehow is differentiated, correct? Somehow it is differentiated. Even you had AX, CX, DX, and so on, correct? So if I talk about this further, I can see that there is SP, BP, SI, DI. Now when I say this SP, BP, SI, DI, if you recall, when we talked about these registers, these are always 16-bit registers. These never, the 8-bit version of these registers can never be found. That's why this AH, CH, DH, BH is added. Now we concentrate on the order of register. EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. Correct? Now how it is? So let us try to see that part. So I'm talking about now the registers. So registers are written like this: EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. Correct. Now the numbers would be taken as 0, 1, 0, 1, 2, 3, 4, 5, 6, 7. Now write them in binary. So you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Correct? Yes? Are you with me?
Yes, sir.
Now if you see here, are these numbers available with that manual too? Now remember, what is EDX? For us, it is 0, 1, 0. See the manual. EDX, this EDX. What is the number associated? 0, 1, 0. So see the numbers given 0, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7. Can you see that? Okay, now let us see this. Same thing would be possibly here. There is a mod given mod 0, 0, 0, 1, 1, 0, 1, 1. Correct. Now let us concentrate on first part ECX EDX. Correct. We have instruction called, say for example, move ECX comma EDX. What is number for ECX in this case?
001.
Very good. 0, 0, 1. What is number for EDX? 0, 1, 0. Correct?
010.
Correct. Now, if you see, what is the representation used for first instruction? D1. Okay, let us write that D1. How you write D1? D1 means what? Now we have to separate them. So each number would be shown by you, what you can call it as. What you can call it as 4 bits. So what is D? D means what in decimal? D is hex. So A is 10, B is 11, C is 12, D is, can I say 13? Am I right? So how will you write 8 plus 4, 12, 13? Can I use this D1 as 0, this 1101 to represent D? Can you display that D as in binary like this only? Because D is what? As per hex 0 to 9, then A 10, B 11, C 12, D 13. So how I took this? So 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. 8 plus 4, 12 plus 1, 13. That's why D. Now 1, 0, 0, 0, 1. Correct. So that's how I wrote this D1. Now if I try to separate this in terms of this mod RM byte notification. So let me go here. Mod RM is written like this. Separate these bits. So 2 bits, 3 bits, 3 bits. So separate them. 2 bits, 3 bits, 3 bits. Now which is 010 in this register list?
EDX.
EDX.
EDX. So EDX is here. Correct. So if second operand is there in the register, that number should be written here. Which is the first operand? Like that means what is whichever is the source would be written here. Which are the destination? Destination is what? ECX. ECX is now what is the number for ECX? 001.
001.
That can be seen here. So we have to write this in cross. Cross in the sense what? Like if ECX, like if this now if for example let us take this another instruction. We'll talk about this EDX ECX. Correct. So let us say EDX ECX. So if it is EDX ECX, how it would be? What is ECX number? 001. What is EDX number? 010. Correct. Now add 11 there. Now you separate them in the group. So what is this? What is this first binary represented hex would be? 8 plus 4, 12. 12 means what? 12 means what in hex? Can I say C?
C.
Correct?
Yes, sir.
Yes. What is 8 plus 2? 10. Correct? What is 10 in X? A. Correct?
A.
Now if you see, one can see in the translation there is CA. Can you see that? Correct. Now if I have EAX, EBX. Sorry. EX, EBX. EBX, EAX, EBX लेते चलो. EX, EBX. Now what is EBX number? 011. What is EX number? 000. Your mod 11. So you group them like this. So this number would be, now see, this is 8 plus 4, 12 plus 1, 13. What is 13? I think D. Am I right?
Yes.
Correct.
Yeah.
D, and this is 8. The second group of 4 bits is 8. So whenever I use EX comma EBX, it should be D8. Let us see whether it is D8. See here. Can you see this? Correct. So now we are somewhere reaching to some conclusion. Whenever there are registers, the register order in mod RM would be picked like this. First thing is, always whenever you have both the arguments as registers, mod would be 1 1. This mod would be 1 1. That's what we got here. See, we got mod 1 1. Because these were the 4 values 0 0 0 1 1 0 and 1 1. These were the 4 values. This one till this one. Correct? So this last is meant for register to register. Is in all these 3 cases we can see 1 1 is occurring as mod. That's why, like if I separate them like this, this is how my register order is. First thing is like first thing about this register to register is mod is 1 1. Order of register given in instruction set would be represented by their respective binary representations in a cross manner. So destination would be written first and source would be written later. Or have I said it wrongly? Source would be written first because move EX comma EBX. What exactly this means? What is source for you? EDX. What is destination? ECX as per our understanding. So if source is there, source should be written first and then number for destination is to be written. Correct. Now if I give you the instructions, okay, let us write this. Take paper and pen with you. Okay, or you can take say you can say any editor or open any editor and you try to write representation for this. EX comma ESI, ESI comma EDI, EDX comma ESP, EBX comma EDI, correct? EX comma EBP, correct? Then EBP comma ESP, ECX comma EDX. Okay, we had already EDX, so let us take ESI, EX comma ESP. Now try to tell me what would be the number. So both of like mod would be what for these all instructions. So mod would be 1 1 for all of them, correct? So we will not write, we will consider that 1 1. Now ESI EDI. Try writing these values. What is ESI above and what is EDI above?
110.
Oh, 1 1.
Oh, first of all, I will write EDI 111 and then 110. So if I combine this as 4 bits together, so I can see that the representation would be what? Can I say FE? Correct?
Yes. Yes.
Yes, sir.
Let us talk about this EAX. So I will add semicolon so that I can add this code as an code letter. Yeah, EAX ESI. Let me know the values now. 11. Mod is 11. ESI number is 110. EX number is 000. Now separate them in 4 bits. So this is F0. Correct? Am I right? What to do EDX ESP? Now ESP first. What is ESP?
100.
Correct. What is EDX? Correct. Now you group it.
010.
You group it. What would be number hex number for this? Yes, what would be hex number for this?
E2. E2.
E2. Correct. Very good. Now what is this? 11 again. EDI. Correct. 111. EBX. So now you group them again. What is this number?
FB.
F. 8 आणि 2 10 आणि 11. F.
B.
B. Very good. Next. बोलो इसका क्या आएगा? 11. EVP. EAX. Group them. What this would be?
E8.
Very good. Okay, next. 11. What is ESP? What is ESP?
100.
Correct.
100.
EBP?
101.
Now group them in 4. What is this number?
E5.
5.
Next. 11. What should I write now?
001.
110.
Carefully see. Carefully see.
001.
No, wrong.
So 110.
Correct.
One
We
zero.
have to take. We have to take number for the second operand. So source. What is ESI?
110.
110.
110.
What is ECX?
001.
Now group them. What is this number?
F1.
1.
F1. Correct. Now last.
100.
1 ESP. 100. Correct. EAX. What is this?
E0.
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 Let us take. Let us copy this. Copy this. Let us go to code. So now I am writing that here. We'll simply write move there in front of each of them. Okay, to only get the idea. So we want to see what are the numbers those are shown. FE, F0, are they matching with this. So if we can successfully get it, that means we already cracked the operand part for register. Correct? Let us see. Let us save this. Let us translate. Let us open the code. Now check whether have you got the same numbers. Where exactly you made a mistake. Is there any mistake?
Yes, sir. No.
So now can you assure me now you understood this part?
Yes,
So
sir.
even if you don't have your assembler with you, you should be able to generate this code, this whole code right now, with assumption that you know that 89 would be used here. So even if NASM is not there, you should be able to do this. Now, how exactly these addresses are calculated? See here. How many bytes it took? So 1, 2. It took 2 bytes. That's why 0, 1 was given. Here is 2. 2, 3, 4 is given. 4, 5, 6 is there. 6, 7, 8 is there. 8, 9, 10 is there. That means A. A, B, C is here. C, D, E is here. E, F. Correct. Next one would be 1, 0. So depending upon how many bytes are used to represent this. So for this case, as per the instruction format, for opcode it is requiring only 1 byte, and that's what is 89. And if you see with 89 in that manual, let me go to that move. After 89, if you see, it has written /r. This /r tells us that there is mod rm byte present. That /r is telling me that mod rm is expected. So now if I don't have NASM with me, if I know the instructions, I have Intel manual, I definitely can translate this code. I definitely can write these addresses with assumption that it starts with 000. I will start writing this. So if even if I am given only this code with the Intel manual, I can generate this code. Whatever you see here, 89FE, 89F0. Is that fine?
Yes.
So now ask questions if you have any.
सर मॉड बिट हमेशा 1 1 ही रहेगी.
In this case, whenever there is register to register, mod would be always 1 1. Now see, we haven't really talked about what you can call it as other formats, right? We are only talking about now register to register. Have I taken any other part of instruction right now? No, because if you recall the code earlier that I wrote that day, like if you see ls-ltr, जो हमने वो pgm2 लिखा था ना, उसमें देखो मेरे सॉरी, इसमें इंस्ट्रक्शन देखो मेरे अलग अलग है. करेक्ट? These are different instructions. I have immediate values here. यहाँ पे register नहीं है कहीं पे भी. So you may have different. That's what it said earlier. Like when you talk about mod rm byte, page number 40. Let us go there. इसके ऊपर जाते हैं. ये जो इंस्ट्रक्शन फॉर्मेट डिस्क्राइब कर रहा था ना, वो वहां पर mod rm का जो देखा हमने. सॉरी. The mod field combines with the RM field to form 32 possible values. Okay, mod field with RM field. RM field मतलब कौन सा था? यहाँ पर अगर देखो, ये RM field, mod and RM field, इनका कॉम्बिनेशन अगर लेते हैं, यहाँ पर कितने हैं?
Excuse me,
8.
sir.
हाँ, या?
Please speak English. I cannot speak Hindi.
Sorry.
I said, please speak English. I cannot speak Hindi.
I don't, your voice is too loud. I am not able to hear exactly what you are trying to tell.
Sir,
I
he
said,
cannot understand Marathi.
Sorry, Marathi, Hindi.
Sir, he cannot understand Hindi, only
Oh,
English.
sorry. sorry. So what I'm saying is, like I want you to see here this mod RM when we have to form this to get those 32 like the values. It is concentrating on 4 combinations of mod. How many combinations are there for RM? 8. Correct? We saw that 0, 0, 0, 0, 0, 1, 0, 1, 0 and so on. So 8 multiplied by 4. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. So if I go on, I would be getting for 0, 0 mod, I would be getting these 8 values. For 1, 0, I would be getting 8, 0, 1, 8, 1, 1, 8. So that's why there would be 32 possible values. That's what it is saying there with mod. Wait, let us see this. Yeah. So it says mod field combines with RM field to form 32 possible values, and those are picked from 8 registers and 24 addressing modes. Now, if you see the form was what? Form of mod RM was you first have mod, then reg, then RM. RM would be towards end. And while we wrote this, we are concentrating this or we are considering this as RM. Correct? We are considering this as RM. So what would be possibilities to have that RM there? So it would be like this. Suppose move EX comma 5. Now in this case, this is source, this is destination. Now exactly, I'm not going to. This would be one form. Second form probably would be what? EX comma EBX. Register, the register immediate. Move EX comma array. This is address. Move EX comma D word of array. So all of them are having different interpretation. This is immediate value first. This is register. This is memory. This is what? Again, value at that memory address. So like I can have multiple forms over here too. So there would be possible, like what are the addressing modes that you have learned into your CO course? All possible forms can be picked. And that's what it is saying, that we can have different 32 combinations for mod RM. Mod field combines the RM field to form 32 possible values by taking into consideration 8 registers and 24 addressing modes. Range opcode field specifies either a register number or 3 more bits of opcode information. So either if it is not a register for range opcode, then the remaining 3 bits would be used to form that opcode. And the purpose of this range opcode field is specified in the primary opcode, because it knows now where exactly it was defined. So if I go to this move, it is specified here 8 9. It says move RS16 to RM16. 8 9 move R32 to R32. That's how it would be happening. Correct? So now I'm assuming that you all are understanding what exactly I was trying to tell with respect to the operands. So if now first thing that we have made it clear for all of us is, if I have register to register as operands for an instruction, no matter what kind of instruction I do have, my mod would be always 1 1. Is that fine? This mod would be always 1 1. You can see this is mod. This 1 1 is my mod. And then the grouping was done like this. Correct? So like if as per the format, first is mod, then what was the other case? So let us go to 40. What is the other part of mod RM? Second part is register. So second part would be register. So this is the register used in this case. Which is the register used there? and then lastly the RM. So whenever you don't see register at the other side, okay, for example here in the RM, then you are going to get something different, which would be constant. So if how many formats would be, how many instructions would be like this? So if I have move EX comma 5, I can write move ECX comma 5, move EDX comma 5, move EBX comma 5, move ESI comma 5, move ESP comma 5, move EBP comma 5, move EDI comma 5. Okay, so let me pick this one below. Fine, so you can see that these would be the 8 possible combinations whenever I have a register and immediate value. Same thing would be true for this as well. Move EX comma array. Same thing would be possibly here for these two. So you may have different forms. So how exactly it is going to differentiate? What would be common? This would be common. In this case, as we said, this is going to define this register field will be important, which is going to get added there with respect to the form. So what is there in the second form? So like when we are talking about our original instruction, whatever value here would be represented somehow here at this point of time in a cross form. In a cross form. Because if you recall, that's how we worked out EX, EBX. This is EX and this is EBX. So we wrote it in cross form to form that D8. Same thing was true for the D1 when we talked about ECX and EDX. Is that fine? Any question? Please ask if you have any.
सर ते असेंब्ली कोड रन केले पण लास्टला सेगमेंटेशन फॉल्ट येतोय.
Okay, don't run that. That's what I'm saying. Now our role is not to execute the code. You should write this instruction only. Our target is this. We don't want to execute that code right now. If segmentation fault is there, I will try to address that afterwards. Our concentration should be now first of all to find out how exactly my code would be translated to object code. Okay. So try this, like for register, try to see, like you write on paper, try to see whether you are getting the same thing on by written by your system. You should see that so that it will be very clear for you to understand exactly what is happening at that side. Is that fine?
Yes, sir.